Hello, so welcome to this video. The last video I made was about geometry and provided a brief overview of some stuff if you're interested in looking at general relativity, for which I would kind of perhaps recommend checking out that video. But today we're going to be looking at a thought experiment, and this thought experiment is within the realms of quantum mechanics. To balance things out, I'm trying to go for roughly 50-50 with relativity and quantum mechanics. But this is an interesting thought experiment, and it really shows how strange quantum mechanics is, because we can actually use quantum mechanics to detect the presence of a bomb, even though it might classically be impossible to do so without the bomb exploding. And we're going to be looking at how quantum mechanics allows us to do this. And we'll be looking at an important feature in which a measurement happens without the transfer of information, which sounds contradictory, and from a classical perspective it would be, but we're going to be discussing that as well as what that implies about the universe. This video has been encouraged to come into existence, as it were, because people like Sabine Hossenfelder, if I'm pronouncing her name right, I do apologise if I'm not, has done a video on this. There's a brilliant MIT course online where they kind of publish some of their lectures, which again discusses the thought experiment. And then there are papers also online which one can read, and I'll be putting the links to some of these papers down below this video, because this video will be going through this thought experiment, but it's worth saying to keep it as approachable as possible. I won't be going too heavily into the mathematics, I'll be just summarising the main parts. But today we're going to be looking at how we can use quantum mechanics to, in theory, see if a bomb is present without the risk of actually exploding the bomb. So we have to think about this experiment that we're going to discuss from the perspective of quantum mechanics. And in this experiment, we put a hypothetical bomb in an interferometer. An interferometer is a device that uses light, or particularly changes in light's intensity, to determine what might be kind of within the interferometer, or things about the different lengths of different paths available to light in the interferometer. So these interferometers are useful, for example, for things like detecting gravitational waves, where the length of a path in one direction might slightly change, allowing a detectable change in the intensity of light that you see at the end. So kind of interferometers are very useful, and we're going to involve them in this thought experiment. But to understand what this hypothetical bomb is going to do to our results that we're going to see at the end, we need to understand how we describe states in quantum mechanics, and how we go about describing kind of the type of states one might see concerning light once it has reached the end of the interferometer. And so for this we use something called state vectors. And now a state vector is a very neat way to describe the states in quantum mechanics. So typically, if we've got a system which has two possible states, we can think about, for example, a coin being heads up as being in the state of heads up and not at all in the state of tails up. So if we think about a vector, we can have how much of the coin is in the state of heads up at the top and how much is in the tails up at the bottom of this vector. And so we write the state of heads up, this classical state, as something like 1, 0, and for tails we represent it as 0, 1. Now it doesn't really matter in which order these things are. The point is that kind of like heads and tails are like mutually exclusive. So where there's a non-zero number for the head state, there's a zero number for the tail state, and vice versa. And these are the only two states for a coin that can exist classically if it's lying flat on the table. However, in quantum mechanics we discuss superpositions of classical states, which in a sense are like states in between two classical states, and these states naturally evolve and change over time, and the Schrödinger equation actually tells us how these states change over time. So, for example, if we have our coin, it might be equally weighted in terms of when we observe it, us finding our heads or tails, and so its quantum state before measurement were done would be an even mixture of heads or tails. And so we get the number in both the tail part of the vector, if you like, and the head part of the vector, that's the bottom and top number, all have the same magnitude. If they don't have the same magnitude, it's still a superposition state, providing both numbers are non-zero. And it's these kinds of superposition states which are key to how we're going to see whether we have a bomb without actually ever any particle interacting with the bomb. Which sounds very strange, but we'll come on to that in a couple of slides. So now we talked about state vectors, we need to look at how we calculate probability of observing a system in a particular classical state from these state vectors. So as a reminder, a quantum system when unobserved is in a mixture of classical states, if you like, or really in between classical states. So we have, for example, this type of quantum state here, and we can ask, well, if a particle is in this quantum state, what is the probability of us finding it in heads up or in tails up? And we have to find it in heads or tails up because those are the only two viable classical states for a particle or a coin on the table. And for some very unknown reason, it seems that nature has decided that whilst things can exist in quantum states when not being observed, the moment observation happens, everything seems to be found in a classical state. So, for example, we can't ask what's the probability, well, we can ask what's the probability of finding this quantum state in this quantum state when we measure it, but the probability is zero. It seems impossible. We always find things in classical states for some reason. So the way that we get probabilities is actually by taking the inner product between the classical state we want to find the probability of measuring the particle in and the quantum state it was in, so psi, the Greek letter that looks a bit like a trident. This psi describes the quantum state the particle was in before measurement takes place. And in the case where we have real vectors, such as for our coin, so each component of the vector is a real number, we can think of that as just a scalar product between the quantum state vector and the classical state vector. And if one does that with heads and tails, one obtains a half because our original quantum state was an even mixture between heads and tails. And this is an example of calculating things from a system in two states. And because lots of things can be in two states, or there are two states which are particularly important, for example, kind of electrons, when they're thinking about bonding, we have bonding and non-bonding orbitals, or bonding and anti-bonding orbitals. And this is therefore a two-energy level system with a higher energy and a lower energy level. We have kind of qubits in quantum computing, again a two-level system. So there are lots of systems where there are two possible classical states available, and so there's actually a lot of study done on them, and one can actually think of all possible quantum states of a qubit or a two-level system, that is a system that has two possible classical states that we can find it in. We can think about the available quantum states as being distributed on this sphere, which we have an image of here, called a Bloch sphere. The closer the state vector is to an axis on the Bloch sphere tells you how much more likely you are to find it in that particular state corresponding to that axis than another classical state. So this has been fairly rapid. Don't worry if you haven't got all the details. The main thing is that we can have quantum states which lie somewhere between classical states, but we always observe things in classical states and we can get probabilities from it. Now, if you've done like the scalar product before with vectors and A-levels maths, you'll be fairly familiar with what the scalar product is, but if you haven't, don't worry. This is just there for those who would like the mathematical nitty-gritty, as it were. The important thing is that these quantum states exist, and we can use this procedure, a fairly straightforward procedure of inner products, or in the case of real vectors, scalar products, to get probabilities from them.
Okay.
Hello, welcome to this second part, if you like, of the video. So the first part we talked about an introduction to quantum mechanics. We talked about how we describe a quantum states as a superposition of classical states and how we find probabilities from that. Now we're going to start to talk about the Bohm experiment specifically, and to do that we're going to have to look at an interferometer. Now, an interferometer is a device that uses light. If we're dealing with waves of light, classically it'd be the intensity of light, to determine something about something that is in the interferometer, and classically this thing would have to interact with the light in order to impact the light. Now, for our purposes with the Bohm experiment, we're going to be considering the case where we're going to be putting in a single photon at a time through this interferometer. So in this interferometer, in a Bohm experiment, there will be the Bohm and a photon. Now, to get an understanding of how the Bohm thing works, it's helpful to think of an interferometer more traditionally, where we don't have a Bohm, we have a sample. And the sample in this case is between our beam splitter and our mirror. Now, the sample has the potential to interact with our photon, and because it will slow the photon down, if we're thinking of the wave-like aspect of the light won't have covered the same amount of the wave cycle it would compared to how much it would if the sample wasn't there. And so the wave will be at a different point to where we would expect it to be if the sample wasn't present. And so the sample introduces a phase shift, we say. That is, it causes the light to be at a different point in its wave cycle. So sometimes a sample is called a phase shifter. Now, to think about how this interferometer works, we have a quantum model and a classical model. So, to start off with classically, and classical thinking is a good point to begin because we build a quantum state from considering the classical states. So, let's have a think about the classical states available to this photon. So, classically, a photon can only take one trajectory. And what that means is when the photon hits our first beam splitter after passing through a lens, which is kind of ensuring this photon travels in the horizontal direction, once it hits the beam splitter, it can either travel vertically upwards or horizontally to the right. It can't travel in both directions at the same time. And because of this, there are two distinct, if you like, classical paths the photon can take. So one path begins with the photon not being deflected by the first beam splitter, but carrying on travelling horizontally to the right. So if the photon's taken this path, it will travel through our beam splitter, hit the mirror on the bottom right hand side of the interferometer. It will then be deflected vertically upwards where it will encounter the second beam splitter. Now if the beam splitters cause there to be a 50% chance of deflecting the photon by 90 degrees compared to the photon travelling along the direction in which it hit the beam splitter, then we would expect for this photon travelling this path for there to be a 50% chance of finding the photon at detector 2 and 50% chance for finding it at detector 1. Similarly, if we look at the other path, if you like, the other classical state, so with this, when our photon encounters the first beam splitter, it is deflected 90 degrees and it travels through our sample. So for this classical state, the photon does encounter the sample, in the other one it didn't. Now, the sample will introduce a phase shift onto our photon. However, this phase shift won't impact how it will be deflected off of the mirror or how it will act when going through the beam splitter. So again, if the photon takes this path, we would expect there to be a 50% chance of it landing at detector 2 and a 50% chance of it landing at detector 1. So in short, the phase shift induced by the sample has absolutely no bearing on the probability of the photon landing at detector 1 or detector 2, no matter what classical state, or in other words, path the photon takes. So classically we would expect our sample to have no bearing on the probability of the photon landing at detector 1 or detector 2. However, quantum mechanically, it turns out that the probability does depend on the phase shift introduced by the sample, and that's because in our quantum state we have two classical states, so that in a sense a photon goes through both paths at the same time, and those two states will have a phase shift between them because one of those states will correspond to the photon not encountering the sample and the other one will correspond to the photon encountering the sample. So there'll be a phase shift between our classical states within our quantum state, and when we take the inner product we'll be mixing terms, and so our probabilities will end up depending on the phase shift introduced by the sample. So that's kind of a discussion, a qualitative discussion, saying how we would expect the phase shift to indeed impact the probability of the photon landing at detector 1 or detector 2, and that is because of interference between different parts of our quantum state with each other. And this idea can be kind of carried forward and is the key to understanding our Bohm experiment. Now, if you're happy with this and you don't want the maths, because you won't need the maths for when I go over the Bohm experiment, then I would encourage you to jump to the next slide. However, for those that would be interested in the maths, I will briefly go through the maths for this traditional Mach-Zehnder interferometer, and though I won't go over it for the Bohm experiment, it's very similar for the Bohm experiment, and I will link below a paper which does have the maths for the Bohm experiment. But I'm picking traditional Mach-Zehnder interferometer because the maths is, I think, a little easier to go over. So for those that would like kind of the maths on exactly how the probabilities depend on the phase shift, I'm going to go through it now. So our first thing is we have two classical states, that's two paths a photon can take. They're mutually exclusive in that classically if the photon takes one path, then it can't take the other path. So we have essentially a two-level system. And so a quantum state is going to be a state with two entries, one referring to one classical state, the other referring to the other. So we have a vector with two entries. And our objects, our beam splitters and our mirrors are going to take the state of the photon and turn it into a different state because they're going to affect the direction the photon is travelling. And therefore they're going to turn one state vector with two entries into another state vector with two entries. And the thing that can do that is a 2x2 matrix. So we'll represent for our Mach-Zehnder interferometer all the things that our photon interacts with via 2x2 matrices. And the first part of this matrix is going to correspond to what happens when the photon goes from travelling vertically, the first part will correspond to what happens when the photon travels horizontally, going to travel horizontally. So in other words, corresponds to the photon just carrying on travelling horizontally after encountering the device. The term on our top right corresponds to our object causing the horizontally travelling photon that hits it to be deflected and move upwards, and the bottom left hand side one, a component, corresponds to a photon that is travelling vertically upwards, hitting our device and being deflected and travelling horizontally, and then our last component refers to the photon travelling upwards before hitting the instrument and then continuing to travel upwards. And we can see that this summarises, if we look at kind of what could happen to our photon in a Mach-Zehnder interferometer, this encompasses everything that can possibly happen to our photon in terms of it carrying along the same trajectory or it being deflected. So we have all the elements we need within this matrix. So if we look at our phase shifter or our sample, so if we look at the term where our photon is travelling kind of horizontally, let's say for example when it's first hitting our first beam splitter, well, it goes from travelling horizontally to travelling horizontally in the case where it doesn't interact with our sample at all and no phase shift is introduced. So for the case where the photon goes from horizontal to horizontal motion, it never interacts really with our sample never introduces a phase shift, so the sample wouldn't change or impact the state impact that classical state at all. So we just have a number 1 because nothing is happening to our state vector. Now for our sample, our photon is going to kind of like only encounter our sample within our interferometer if it was travelling up vertically upwards before hitting the sample and is travelling vertically upwards after hitting the sample. In our kind of setup, we're not worrying about scattering or reflection or any of that. And so the off-diagonal components of our matrix are going to be 0 because our sample isn't causing any deflection of our photon. So that's where the number of zeros come from. And then our last element corresponds indeed to the photon interacting with our sample, because for the photon to do this, it has to be travelling vertically upwards to meet the sample, and then we're assuming our sample absorbs the photon and re-emits it sometime later, and so it goes from travelling vertically upwards to travelling vertically upwards. And so our sample will introduce a phase shift. However, the sample, when it's introducing the phase shift, it won't cause the photon to be any more likely to have gone into the to be found in the classical state if we were to try to observe it early on in its journey, where it did pass through the sample compared to it not having passed through the sample. And therefore, our sample shouldn't change the amplitude of the classical state, referring to the photon encountering the sample. And therefore, the sample has to not change the amplitude, and therefore the number corresponding to the effect of the sample has to have a magnitude of 1. However, as we said, the photon does change its phase shift, so we want a function whose magnitude will always be 1, but is still a function of the phase shift, or delta phi in Greek letters. A function that does that is the unit complex number, which is free to depend on the phase shift, or delta phi, but which by definition is always of unit size. So it won't actually, the amplitude of the classical state won't be altered by this phase shift. And EI to the phase shift, or EI delta phi, is indeed that unit complex number. As you will know if you've done kind of complex numbers before. So that's our phase shift. Now our mirror, so sorry, not our mirror, sorry, our beam splitters. So if we look at what's happening with our beam splitters, so our beam splitters can essentially, we're going to assume, have a 50-50% chance of deflecting the photon compared to not deflecting it, hence the 1 over square root of 2. It corresponds to getting a probability of a half to do with it going one way or the other way after the photon has hit the beam splitter. As you know, using similar maths to what we did before, one could show that. So that's where the that's where the factor 1 over square root of 2 comes from. Now, because our beam splitters we're assuming don't introduce any phase shift, if the photon was travelling in one direction before hitting the beam splitter and continues to travel in that direction after hitting the beam splitter, then nothing has happened to the state of our photon. So we will have a number 1 corresponding to cases where the direction the photon is moving in hasn't changed. Hence the diagonal terms of our matrix for our beam splitter have to be 1. However, our beam splitter also has a chance of deflecting our photon. Now, deflecting it, it's deflecting it by 90 degrees, so it's changing its phase shift by 90 degrees, or pi by 2 radians. And to be consistent with our phase shift matrix, so our matrix squaring the sample, we said that the phase shift was given by EI delta phi, or EI phase shift. So if the phase shift is pi by 2 radians, then the matrix element we want corresponding to this phase shift is EI pi by 2, and that is indeed the imaginary number I. So the off-diagonal components of our matrix for our beam splitter are going to be I. So we now have are matrices describing how the state of a photon is or is it altered. And so now we can get probabilities. So for the probability of finding a photon going to detector 2, and that is its last step being to be travelling upwards, what we do is we take initially, because initially due to the collimated beam or lens, the photon has to be travelling horizontally initially. So it starts in classical state travelling horizontally, and that's what psi-L is. And so travelling horizontally, if we look at our matrix, that's going to be like 1 at the top and 0 at the bottom. So that's our initial state vector, and then it encounters our beam splitter, and the beam splitter is going to change our classical state into a quantum state, and then we put this quantum state, we act this quantum state on our matrix with the phase shift, because remembering a part of this quantum state will refer to the photon encountering the sample, so we need the phase shift matrix, and then after that it encounters another beam splitter, so we have to then also multiply by our beam splitter matrix. And then once you do all of that, what you end up with is your final state of the photon, and to get the probability of measuring the photon in detector 2, what we have to do is we have to take the inner product between the classical state referring to the photon going up or landing detector 2 with our final quantum state, superposition quantum state before the measurement happens. And to repeat, that final quantum state is given by taking our initial classical state and then altering it using our beam splitter matrix, our phase shift matrix, and another beam splitter matrix. And once one goes through all that maths, one ends up with this expression for the probability of the photon landing in detector 2. And indeed, we see that this does indeed depend upon the phase shift. And one can do a similar thing with the probability of the photon landing in the lower detector or reaching, in other words, detector 1. And again, this depends upon phase shift. And another way you can get the probability of it landing in detector 1 is you can go, well, we have to either measure the photon in detector 1 or 2, because we have to find it in one classical state or the other, meaning that the probability of our photon landing in detector 2 plus the probability of it landing in detector 1 must equal 1, because we definitely find it in one of the detectors. Find that it has interacted with one of the detectors. And so if you know the probability of it hitting one detector, you can immediately find the probability of it hitting the other. And for those of you who are familiar with trigonometric identities from A-level maths, you will indeed know that if we add our two probabilities here together, we will get 1 no matter what phase shift the sample induces. So that's how one will go through the calculation, and one can do a very similar thing for a bomb. I will not be going through the maths for the bomb here, but as I say, I will put a link to the paper. But the good thing when going through this maths is we can see very clearly that due to the quantum state induced, the moment our photon hits our first beam splitter, as well as that being sustained through this experiment, we do get probabilities that depend upon phase shift. And that is the probability, even though we have a single photon, does depend on the phase shift introduced by the sample. And as a side note, because this comes from different parts of the quantum state interfering with each other, we say, in other words, that the photon is like self-interacting, because different parts of its state is interacting with each other, even though the photon, we just have one photon in our interferometer at any time. So to summarise, we're going to talk about what we learned from the interferometer and quickly move on to the bomb. So from the interferometer, we know that we find the photon at only one detector, and also due to the conservation of energy, which broadly works in quantum mechanics, without going into too many subtleties. We can also say that we can't say that during the experiment the photon was actually literally in two classical states, because that would violate the conservation of energy, because before it enters a quantum state we have one photon with one energy, and when we detect it, we detect a photon with the same energy, or at least detect the interaction associated with the photon with that energy. And if in between we actually have the photon in both classical states, travelling in both paths in a very literal way, we would in a sense have double the energy of our photon in our system. So our conservation of energy would be violated, both between the photon kind of going on its long way after passing through the lens, and also to do with afterwards when we measure our photon, because there'd be an inconsistency in the energies. So at least, and indeed because we find the photon having interacted with only one detector, the photon, once we measure once we determine what detector it's interacting with, does seem to have interacted with only one detector, and as we say, due to the conservation of energy, this could kind of imply also that it's only travelled along a single path. However, despite that, the probability of the photon landing on a detector is influenced by this self-interaction. In other words, it's influenced by parts of the quantum state corresponding to things that the photon has never seemingly done after we've observed it. So in that sense, what we observe depends not only on what the photon has done, but also what it has not done. It's a very peculiar feature here of these interaction-free measurements. And this kind of like interaction-free novelty, where the state of a photon depends on both parts of its quantum state, including parts corresponding to the photon doing things that, at least after measurement has occurred, it seems never to have done. It is a key to understanding the Eliza-Reutemann-Bohm experiment. So now we're going to talk about a Bohm experiment. Now for this, what we're going to look at is just what happens if we place a bomb in our interferometer, and we want to determine, is there an active bomb in our interferometer? And by active I mean if any photon interacts with this bomb it will explode. And our challenge is, can we use quantum mechanics and our interferometer to determine if there is this active bomb in our interferometer using photons without the bomb exploding. Now classically this can't happen because, as we say, if a photon interacts with a bomb it will explode, and classically to determine whether a bomb is present using photons, our photons would have to interact with the bomb. But as we've seen quantum mechanically, the final state, where the probability of finding the photon at detector 1 and detector 2 depends not only what does happen, but what doesn't happen. And so there is a probability of the photon confirming that there is an active bomb in our interferometer, even though the photon has never interacted with the bomb. So we set up our interferometer and we design all the paths and mirrors, for example, such that when there is nothing, so we've got now an interferometer and there's no sample in the interferometer, but so we've got an interferometer with like no sample, or for now no bomb in it, and we design it such that when there is nothing, whether there is a bomb or a sample, then when we single photon photon through, we will know for certain, due to deconstructive interference from different parts of the quantum wave function, that the photon will have to arrive at detector 2. And we can easily do this by just setting up the paths to ensure that there is deconstructive interference corresponding to the photon landing at detector 1, so the probability is 0, and that way we know for certain the photon will arrive at detector 2. Then what we do is we place a VOM in the lower part of interferometer. So for our sample, we placed it on the vertical part of interferometer. For our VOM, it's on the lower part of the interferometer. Now, to see what's going to happen, although I won't go through the maths, it's worth talking about this qualitatively. If a photon was to, if we think of the classical state corresponding to the photon hitting the bomb, so if the photon was going to exist in this classical state and did hit the bomb, then the bomb would, as we said, explode, meaning the photon would be scattered, and so the photon wouldn't actually arrive at detector 1 or detector 2. It would just kind of like leave our interferometer altogether. There's a very, very high chance, so essentially almost certain that our photon will never arrive at detector 1 or detector 2. Now, it turns out that this fact that if the photon was to interact with the bomb, it would be scattered and not detected at detector 1 or detector 2, this introduces a possible classical state, which, when going through the same procedure we did before, and bearing in mind that our photon is actually in a quantum state, a superposition of classical states, actually there's a scattered part to our wave function or state vector, and this is going to remain present in its quantum state until our observation occurs, by which I mean the photon is either found at detector 1 or detector 2, and bearing in mind the scattered part of the wave function remains present even long after we're looking at the point where the photon could have encountered the bomb. It only goes away once the photon decides to interact with detector 1 or detector 2. And so due to this, the scattered part of the state vector is still important, and one can go through the maths, and indeed it turns out that there will now be a probability of the photons arriving at detector 1 if the photons did get scattered. And we're assuming that if there is at the bombing experiment, as we said, we set up our experiment such that the photons will all arrive in detector 2. However, if we have found photons in detector 1, then, well, they've never been scattered, so they've never interacted with the bomb. So in other words, we can have a situation where there's a probability of finding our photons at detector 1, but if they do land at detector 1, we know for certain that the bomb is present because it's only due to this scattered classical state within our quantum state that would allow for the probability of our photons landing at detector 1. However, because we see our photons at a detector, the bomb hasn't exploded and the photons have never been scattered. So in other words, we've determined that our active bomb is there using photons, even though our photons have never triggered the bomb and therefore never interacted with it. And it sounds mind-boggling, it is, but that's how strange quantum mechanics is for you. Now I will talk about how to adjust this such that, well, yeah, we'll see in a bit. But as I say, photons arriving at detector 1 correspond to the bomb being present, but the photons never actually encountering the bomb. at all. It's strange, I know, but there we are. So we talked about how to test whether there is a VOM that we know if it is present is active in interferometer, but the thought experiment was mainly about, well, how do we test whether a VOM is active in our interferometer? So it's a similar idea to before, save now we consider the chance where there might be a VOM there, and if a photon interacts with the VOM, it will the VOM might explode. And if it's active, in which case the photon will get scattered. Or classically speaking, if the VOM is not good, the photons will just pass through the VOM, and we're just assuming in this very idealistic case they'll just pass through the VOM and won't set it off, and the photons won't be affected at all. So as I say, we now assume that some VOMs have sensors that aren't working, allowing for photons, in the case where the sensors aren't working, to travel through the lower half of the interferometer. So it's very similar maths to before. So what we want to do is we want to maximise the probability of the photons being found in the detector that will correspond to the VOM being active. But we want to minimise the probability of our photon ending up being scattered and never arriving at detector 1 or detector 2, because remember, if a photon ends up in a scattered state, that means the VOM has been triggered, so we have an explosion. And we can do this by changing the reflectivity of the mirrors, and if we want to go even further, we can put our VOM in a cavity, and we can actually get to the point where we have a pretty good chance of actually determining whether our VOM is active or not without much risk at all of the VOM exploding. So that's the VOM experiment for you. Now I know this is very, very strange. This bit of physics is very, very odd, and it's an intriguing bit of physics. But that's the magic of really quantum mechanics. It's very unintuitive because it depends on, at least via the Copenhagen interpretation, or some versions of it, what doesn't seem to happen as well as what does. One of the many reasons why it's worth thinking about alternative ideas to the Copenhagen interpretation, because although the maths works, it does seem very odd, and indeed it makes sense to question the physicality of this, and to think, is there any way else of interpreting the maths? So I hope to do a video on interpretations of quantum mechanics soon. This has been a fairly long video. Now I hope after watching this video you go outside, go for a bit of exercise, maybe have a run, go for a walk, enjoy the sun whilst we've got the sun, and I'll hopefully see you for another video soon, and thank you so much for watching. And if you haven't got to the end, well done. I know it's been very abstract, but hopefully quite kind of intriguing too. I hope you've learnt something about self-interaction, and though hopefully you will never need to. If you now ever do need to test whether the VOM is active, you at least know an experimenting theory of how to do it. But anyway, hope you have a good day, and yeah, I shall hopefully see you in more videos soon.